All right, and welcome to another Vendor Spotlight series here at RefComm and Coking.com. We are here on the shop floor with our friends at MOGAS, and we are going to be talking about their coker switch valve and some of the unique technologies that they have brought to the market. And I'd like to introduce next my friend Michael Lemeshev. He's with MOGAS, and he and I are going to talk about some of the unique aspects of this particular valve. It is a 4-way or 3-way valve, depending on who you talk to, switch valve for the delayed coker industry, specially designed. So Michael, if you could just give us just the very briefest highlights of some of the design features of this valve.
You bet, Evan. Thanks very much for having us. Appreciate that. So let's start off with one of the topics that I think most folks find to be extremely important in this valve design, and that's the purging design, the purging and the drain. So over here you'll see we have a couple of purge inlet ports. On the back side we have an additional couple of purge inlet ports, and then over here on the bottom, and then another one at 120 degrees from this drain port, we have 2 drains. So purge inlets here and here, and drain outlets there and there. So that's the first important aspect of the valve. Then, as Evan mentioned, this is a 4-way valve, so you have an inlet through the bottom and 3 outlets at 120 degrees from one another. Internal to the valve, you can see the flared out design, so you can actually see that the ball, or the hole in the ball, is bigger than the actual line ID, and that's done for a specific reason. In here you'll also be able to see what we call our semi-trunnion design. We'll go into some detail on that, so that's another very important aspect of the valve. And then coming up here through on the actuator side, we'll also discuss some of the things that you can do to monitor the health and the actual stroke location of the valve in a very concise way, with a connection between the actuator and the physical indicators up on the top of the valve, on top of the actuator. So,
well, Michael, thank you for the brief introduction. I think we're going to segue directly into that trunnion discussion, because I feel like that's something as a unique aspect of your valve that I want to make sure the viewers have a better understanding on. So you talk about the trunnion. So the trunnion, if we get down in there, and we're going to add some graphics to this later, but if you get down in there, you see that the actual ball itself extends down slightly, and there's a sleeve piece that goes in there that you call a trunnion, and it's a slightly different design than a trunnion valve per se. So can you help us understand exactly how that trunnion is laid out and what it's meant to do? So if we look in the inside there, you can see it, and we're going to try to put a better picture in there for the folks at home. But how does this actually work?
okay, so the idea of a trunnion valve is that there's a shaft on the top that connects to the actuator, and then on the bottom there's also an additional shaft holding the ball in place. Well, of course we can't have a traditional shaft in a DV4 or a coker 4-way valve, because the flow comes in through the bottom.
Sure, yeah.
But so what we did is we actually created a piece of pipe that literally inserts through the bottom, through the center of which the flow can go, but also this piece of pipe inserts into a boss at the bottom of the ball itself, thereby creating a smooth flow transition from the flow as it comes into the valve into the ball area itself. So there's really no opportunity for the media to encapsulate the ball on the outside of the ball and the ID of the body, which we've minimized quite significantly. We'll be talking about that as well with this very specific bonnet design, right? So the this pipe acts like a trunnion, in effect holding the ball centered in this configuration, so that no amount of pressure acting on the ball surface will push this, let's call it a lollipop, right? Because essentially that's what it is, right? It's the ball and the stem configuration. This lollipop can't ever be pushed in any direction, no matter what side the pressure is acting on, because that center pipe, if you will, that piece of pipe is holding it in place.
And there's a metal to metal overlap.
That's correct.
On there, and that lower leading edge of the trunnion sleeve is held in place against the ball on the one side, and then it's also pushed down
into the body, into the actual corpus of the valve, into the cast part of the valve, right? So it's actually, so the flow never actually sees the ID of the body itself.
Yeah.
It's always seeing the trunnion pipe piece itself. Right.
So the flow comes in and it's forced. It doesn't have any opportunity to get to the outside.
That's exactly correct.
Right.
That's
Okay.
exactly
Well,
correct.
I think that's definitely one of the unique features of your design here at MOGAS. And so I'd like to talk a little bit more about what's going on with this upper bonnet. For folks who are familiar with other ball valve designs, you'll notice that this upper bonnet arrangement is very different.
Right.
So walk us through a little bit about how you arrived at this particular layout and what's going on the inside here.
There's a couple of things here. So there's minimizing the area or the space between the OD of the ball and the ID of the body. So think about that. Think about the massive amount of space that can be between those two components. And then secondarily, we really want to make this valve field serviceable. Right? So that's a key aspect of this. So you can see it's quite a significant flange thickness here on the top. This entire assembly can come up, and as it does, it actually reveals internally the stem spring arrangement, so that in line, without unbolting the valve from the line, you can actually start to remove the springs and the seats. And once you do that, then you can remove the lollipop configuration.
Yep.
So that's one aspect of it. But then the other aspect of it, and we heard this actually in a number of your very informative conferences, and that was that there's a significant amount of ingress of, let's say, this media, this very sticky media, into the corpus of the valve. You don't want to minimize that as much as possible, because the more of that gets into the body of the valve, and if it gets a chance to cool off, right, it can turn rock hard. So if we have just a very minimal amount of space between the OD of the ball and the ID of the body, we felt like that would be a huge boon to keeping the valve from sticking. Right? And so we've designed this bonnet arrangement in such a way that there's virtually no space between the ID of the body and the OD of the ball.
Well, some people know that these valves live and die based on steam, right? Steam purge is the way that these things stay healthy. And by creating this relatively small space, you've minimized the amount of material that can accumulate in there, but you also maintained a variety of different purge configurations that we've talked about separately to understand how to purge that body away of the material that can solidify in there and cause coke and cause trouble, right?
A significant amount of reduction of the volume of steel that's necessary to keep the body cavity pressurized. Does that make sense?
So one of the things that we've seen in the field and in various maintenance situations is that sometimes that material, when it accumulates on the body of the ball in that kind of that cavity, that void space, it kind of creates a bit of a brake pad, if you will, a sort of resistance for force that you then feel and experience with the torque at the actuator, and that tells you that the valve's getting sick and needs to be repaired eventually, right? So, but how does this layout with the relatively small negative space impact that, let's call it a braking effect that we experience as torque?
So it's interesting, right? So we've got a number of these installed in service now, and we actually haven't seen actuator torques increase over periods of the last 12 months, right?
Okay.
And the valve has seen some, let's say, troubled operations in some cases, where there's been there's, for example, been loss of steam purge, and you potentially could envision where let's say there could be some sort of hydrocarbon between the OD of the ball and the ID of the body. By minimizing that space, you actually have created a much more, let's say, advantageous shear point, or shear what would you call it, the barrier, or maybe that interface, where you don't have a huge amount of coke that can really solidly solidify. You really have a very insignificant amount of hard coke that can only build up in there. And you're shearing that every single time you stroke the valve.
Yep.
Right? There's no opportunity for large chunks of coke to stay unsheared, and eventually, as you know, with hydrocarbons, especially at this temperature, right, they'll start to cook out, and the coke will become harder and harder and harder over time. This just can't happen with that small little annulus there. The coke just doesn't have the opportunity to cook each time it's shearing.
Interesting, interesting. Well, there's a lot of unique design aspects to this valve, and I don't know if it's obvious from you at home viewing this, but this assembly right here is on a pallet for a reason, because they're going to bring this entire thing to RefComm.
That's right.
And they are going to have demos. It's got a live actuator back there. The valve will cycle. You can learn more about it. Michael Lemeshev and the rest of the MOGAS team will be at the event in Galveston
We will.
with this very large, beautiful valve. And thank you for sharing a little bit of the design features, and we look forward to learning more about your technology in the future.
Thanks, Evan.
Thank
Appreciate
you.
it.